Like you're waiting for some news, maybe, and all the possibilities feel sort of real.
Exactly, that feeling. Well, it turns out that down at the tiniest scales of reality, before we actually, look at something, things aren't just uncertain, they're kind of genuinely existing in a mix of all those possibilities.
It's pretty mind-bending, isn't it? That this fundamentally weird behavior is actually the basis for, well, everything we see around us.
Right. And today, that's what we're diving into.
Yeah.
One of the biggest head scratchers that comes out of this quantum world.
Which is how a measurement actually happens. Why do we see just one definite thing when the quantum rules seem to allow for so many options?
We're unpacking quantum measurement and the whole idea of wave function collapse.
Yeah.
Now, I know that sounds maybe a bit heavy, like diving into a dense physics text.
It can sound intimidating.
But that's not the plan. Our goal here is really to pull out the fascinating ideas, the sort of aha moments,
Make it clear, make it intriguing.
Exactly. You shared some great sources, and we've boiled them down to what we think are the key insights for you.
So let's get straight into it. What's the situation with a quantum particle before we mess with it? What's its state?
Yeah, what's it doing?
Okay, so before any measurement, a particle, let's say an electron, doesn't really have a definite position or a definite spin, not like a tiny billiard ball.
Right.
Instead, its state, everything we can know about it, is described by this mathematical thing called the wave function, usually written as that Greek letter psi.
So the wave function isn't just saying we don't know the spin yet. It's more fundamental.
Much more. It's like the universe itself hasn't committed to a specific spin value until we interact with it. The wave function describes this state of potentiality.
That's a pretty wild shift from how we normally think about things.
It really is. The wave function represents what we call a superposition. It's a mathematical combination of all the possible states that the particle could be found in if we were to measure it.
Like the electron spin example you mentioned before.
Exactly. If you measure an electron spin along some direction, you'll always find it either spin up or spin down. But before you measure...
It's both, kind of.
It exists in a superposition, a state that's a mix of spin up and spin down at the same time. It's like it's holding both possibilities simultaneously.
Okay, and that's where we see that equation, right? AE equals AC times spin up plus OP times spin down.
Yeah.
AAO plus AAA. Looks complicated, but what are the pieces?
Yeah, let's break that down. The AA bit is just physics shorthand for the spin-up state.
Okay.
And cherry is the spin-down state. Simple enough.
Got it.
Now, those Greek letters, AA, alpha, and beta, those are the interesting parts. They're called probability amplitudes.
Probability amplitudes, not probabilities themselves.
Not quite. They're complex numbers, actually, but the key thing is they determine the probabilities. Think of them as encoding the amount of each possibility spin up and spin down present in the superposition.
So they hold the potential for the odds.
Exactly. The wave function, with these amplitudes, doesn't tell you what state you'll find. It tells you the probability of finding each state if you do a measurement.
How?
That's where the Born rule comes in, named after Max Born. It's super simple, actually. The probability of getting spin up is the amplitude alpha squared. Well, technically it's absolute value squared.
Okay, yeah.
And the probability of getting spin down is 1.
And those probabilities have to add up to 1, like 100%.
Precisely. Not plus 1, which just means, well, you're guaranteed to find one of the outcomes when you measure. It has to be either up or down.
It's like that quantum coin idea. Before it lands, it's not heads or tails, but this superposition and the amplitudes tell us the chance of heads versus tails when we look.
That's a great analogy. And this state of being both at once with this specific mathematical relationship between the possibilities, that's called coherence.
Coherence.
And that coherence is absolutely crucial. It's what allows for things like quantum interference, where a particle seems to interfere with itself. It's the quantumness of the situation.
All right, so we've got our particle in this fuzzy superposition state described by the wave function. Coherent possibilities.
Yeah.
Now, how do we get a definite answer?
Yeah.
That's measurement, right?
Yes, measurement is all about interaction. You need a macroscopic measuring device, an apparatus, to interact with the tiny quantum particle.
Something big enough for us to see the result on.
Exactly. And it's designed specifically so that the particle's quantum state gets linked to some clear classical state of the device. A pointer position, a light flash, something unambiguous.
Can you give some concrete examples? What do these apparatuses look like?
Sure. If you want to measure where a particle is, you might use a photographic plate or maybe a digital CCD sensor. The particle hits it, leaves a dot, definite position.
Okay.
For spin, like we've been discussing, the classic example is the Stern-Gerlach device. It uses magnetic fields to physically push spin-up particles one way and spin-down particles another way.
So it separates them based on spin.
Right. And for light, for photons, if you want to measure polarization, is it vertically polarized or horizontally polarized? You'd use a polarizing filter and then a detector behind it. Does it go through or not?
These are the tools. But wait, these measuring devices.
Yeah.
They're made of atoms and stuff too, right? They're quantum underneath.
That's a really sharp point.
Oh.
Yes, fundamentally, they are made of quantum constituents, billions upon billions of them.
But they don't act all fuzzy and superposed.
Well, because they're macroscopic, they contain so many particles interacting in complex ways they behave, for all practical purposes, classically. Their states are stable, definite, and needle points here. A detector clicks or it doesn't. It's not in a superposition of pointing here and there.
Okay, so the quantum particle meets the classical acting apparatus. What happens when they interact?
This is where entanglement enters the picture. It's absolutely key.
Entanglement, okay.
Yeah. Let's use the spin example again. Say the apparatus starts in a ready state. We write that as ready Z. Before they interact, the whole system is just the electron superposition next to the ready apparatus. Ashes plus ashes.
Ahs. That little O-time sign, that just means they're part of the same system description.
Yeah, it's a tensor product, basically saying these two things are together in the description. Now, when they interact,
What happens?
the electron spin state gets correlated or entangled with the apparatus state. The whole system evolves into a new superposition. Ashi is pointer up plus Fesha pointer down.
Whoa, hang on. So the superposition didn't vanish.
Nope.
Now the whole combined system is in a superposition. The electron and the pointer. The pointer is somehow pointing up and D down at the same time, linked to the electron state.
You got it. That's exactly what the standard quantum math predicts. The spin-up electron state is now linked exclusively to the pointer up state, and spin down is linked to pointer down. The superposition now includes the macroscopic pointer.
That seems even stranger. Why don't we ever see pointers in a superposition?
Because we haven't considered the rest of the universe yet. The environment.
Right. The outside world that always gets involved, doesn't it?
It's unavoidable, especially for a macroscopic object like a measuring device. It's constantly interacting with air molecules, thermal radiation, vibrations, countless tiny interactions.
So the entanglement spreads.
Very, very quickly. The particle is entangled with the apparatus, and then the apparatus almost instantly becomes entangled with trillions upon trillions of particles in the surrounding environment.
So that equation gets even bigger. Like on our environment, one area environment, one area environment, environment to area, something like that.
Schematically, yes. And the crucial thing is that those environmental states, environment 1 and environment 2, which get coupled to the different pointer states, they become almost perfectly distinct, practically orthogonal in mathematical terms.
Like completely different environmental fingerprints for each outcome.
A good way to think about it. There is basically zero overlap between the environmental state correlated with pointer up and the one correlated with pointer down.
Okay. And what does that do? This rapid entanglement with the environment.
This is the process called decoherence, and it's incredibly important
Right,
because we as observers can only really track the particle, and the apparatus keeping tabs on every air molecule is impossible. This entanglement with the environment effectively scrambles or washes out the delicate phase relationship, the coherence between the pointer up and pointer down parts of the superposition.
So the quantum bosuness gets kind of lost, distributed into the environment where we can't see it.
Exactly. The information about the superposition gets diluted into the environment's vast number of degrees of freedom. It suppresses the ability of those macroscopic states, pointer up versus pointer down, to interfere with each other.
So decoherence makes it look less quantum.
It makes the system behave, for all practical purposes, like a classical statistical mixture. It acts as if it's either spin up A and D pointer up with probability a car, or spin down A and D pointer down with probability ow.
Okay. So that's why we don't see Schrödinger's cat being alive and dead.
Yeah.
Decoherence picks a preferred state.
It explains why we don't see macroscopic superpositions. Yes. The interaction with the environment rapidly selects a preferred basis in this case, the definite pointer positions, and makes the system look like a classical set of probabilities for those positions.
Okay. Decoherence explains why things look like classical probabilities. That makes sense. But It doesn't actually pick one outcome, does it?
Yeah.
We still only ever see the pointer definitively up or definitively down, not the probability mix.
You hit the absolute core of it. That's the measurement problem.
Right.
Decoherence takes us from quantum superposition to something that looks like classical probabilities, but it doesn't explain why in any single experiment we get one single specific result, why this outcome and not that one.
And that's where all the different interpretations of quantum mechanics come rushing in to try and explain that final step.
Precisely. They try to bridge that final gap between the probabilistic description after decoherence and the single definite reality we perceive.
Starting with the oldest one, kind of the default for a long time, the Copenhagen interpretation.
Right. Developed by Bohr, Heisenberg, and others. Copenhagen basically says, upon measurement, something special happens. The wave function undergoes an instantaneous, irreversible collapse.
Collapse, like it just pops.
Poof. The superposition just ceases to exist. The wave function abruptly changes to represent only the single state that was actually observed.
So in our example, odd quarter pointer up says plus pointer down if we see spin up.
Copenhagen says the whole wave function instantly becomes just S-Twine or upsa. The other possibility, the A term, just vanishes.
And the chance of that specific collapse happening is?
Given by the Born rule again. It collapses to the spin-up outcome with probability arise, or to the spin-down outcome with probability arise.
What causes the collapse in the Copenhagen view? Is it the observer, the apparatus? It sounds a bit arbitrary, like a rule added on.
That's the big criticism, and a valid one. Copenhagen doesn't really provide a physical mechanism for the collapse. It's treated more like a postulate, a fundamental rule of how quantum mechanics interfaces with the classical world, or with measurement. And defining exactly what constitutes a measurement that triggers collapse can be tricky.
Which naturally leads people to think, maybe there's no collapse at all. Like in the many-worlds interpretation, that one sounds wild.
It is wild, but it's also mathematically quite elegant in some ways. The many-worlds interpretation, or MWI, championed by Hugh Everett III, says, forget collapse, it never happens.
Never.
Never. The wave function, described by the Schrödinger equation, always evolves smoothly and deterministically. Always.
So what happens when we do a measurement then, if there's no collapse to a single outcome?
When the measurement interaction happens, creating that big entangled state like unschreiner upsilon 1 nava plus weiner un of 1 1ville, the entire universe splits.
Splits into parallel universes.
Essentially, yes, it branches. One entire branch of the universe forms where the outcome is spin up, the pointer reads up, the environment reflects that, and the observer in that branch sees spin up.
It's simultaneous.
Simultaneously, another branch forms where the outcome is spin down, the pointer reads down, the environment reflects that, and the observer in that branch sees spin down.
So, every possible outcome of every quantum measurement happens in its own separate universe.
That's the core idea. All possibilities encoded in the wave function become physically real, just in different, non-interacting branches of reality.
And decoherence is still important here.
Absolutely crucial. Decoherence explains why these branches, once formed, effectively can't see or interact with each other. They rapidly become distinct and evolve independently. So the U in the spin-up branch has no awareness of the U in the spin-down branch.
Wow. That avoids the collapse problem by just making everything real somewhere.
It's a very different ontology, a different view of what reality is.
Okay, what about other alternatives? You mentioned objective collapse theories.
Right. These are different. Theories like GRW, Ghirardi-Rimini-Weber, or Penrose's ideas suggest that maybe the Schrödinger equation isn't the complete picture. They propose modifications to it.
How so?
They add terms that cause the wave function to spontaneously collapse on its own, randomly, without needing an observer or even a measurement device, strictly speaking.
A real physical collapse process.
Yes, and the key idea is that this spontaneous collapse is extremely rare for a single particle, but it becomes much, much more likely and happens extremely quickly for systems with many particles, like a macroscopic measuring device.
Ah, so that explains why big things are definite, but small things can be in superposition.
Exactly. The collapse is just part of the fundamental dynamics, happening all the time, but becoming dominant for large systems. And decoherence actually emerges naturally from this process, too.
Interesting. And the last one you mentioned was Bohmian mechanics. Pilot waves.
Bohmian mechanics takes a completely different route again. It says particles, like electrons, always have definite positions. Always.
Always. So no superposition of positions.
No superposition of being in multiple places. But there is still a wave function, the pilot wave, which is considered a real physical field that guides the particle's motion.
So the particle has a definite spot, but the wave tells it where to go.
Precisely. And the wave function still evolves according to the Schrödinger equation. Measurement in this picture isn't about collapse. It's simply about the apparatus interacting with the particle and revealing its pre-existing definite position or property derived from it, which was determined by its trajectory guided by the pilot wave.
So where does the quantum randomness come from in Bohmian mechanics?
It comes from our ignorance. We can't know the particle's exact initial position perfectly. Tiny uncertainties in the initial position lead to vastly different trajectories because of the guiding wave, making the outcomes look random, even though the underlying process is deterministic. It's sometimes called a hidden variables theory, the initial position being the hidden variable.
Okay, wow. Let me try and recap this journey. We start with a quantum particle, fuzzy, in superposition.
Described by the wave function, yeah.
It bumps into a measuring device, gets entangled.
The superposition spreads to include the device.
Then the environment gets involved, causing decoherence.
Which makes the combined system look like a classical set of probabilities for definite outcomes, washing out the macroscopic quantum weirdness.
But then we hit the wall, why only one outcome? And that's where the paths diverge.
Exactly. Copenhagen says collapse happens, deal with it. Many worlds says everything happens, the universe branches. Objective collapse says collapse is a real physical process built into the laws. Bohmian mechanics says it was always definite, guided by a wave.
That's a fantastic summary. Decoherence seems pretty well accepted for explaining the classical appearance.
Yes, the physics of decoherence is relatively solid and experimentally supported.
But the interpretation of that final step, the Y1 result, that's still very much debated.
Deeply debated. It touches on the very nature of reality, observation, and information.
So the big takeaway feels like measurement is this absolutely critical link. It connects the weird probabilistic quantum realm to our everyday world of solid, definite things.
It's the bridge.
But how that bridge actually works, the exact mechanism that selects one reality out of many potentials, that's still one of the deepest mysteries we have.
It absolutely is. And it leaves you, the listener, with a pretty profound question to chew on, doesn't it?
Which is?
Does the act of us looking, of observing, fundamentally change what's real, like Copenhagen or maybe even MWI implies in a way? Or is the outcome already decided somehow, hidden from us until we uncover it, like Bohmian mechanics suggests?
It makes you reconsider that initial feeling we talked about, multiple possibilities hanging in the air. Maybe that's not just psychology. Maybe it's a hint of the quantum reality underneath, where all those paths are, in some sense, simultaneously trying to happen.
That's a really poetic way to put it. And hopefully this deep dive has given you some tools, some ways to think about these incredible questions at the heart of modern physics.
Absolutely. It really hammers home that when we observe the universe, well, the act of looking seems to be far more involved, far more fundamental than just passively seeing what's already there.